Hello, welcome to the Active Control Method for Accelerated Vortex Dissipation Senior Design Project. My name is Kylie Skirdo, and I am the team lead for this group. Tin Nguyen, Riley McClurkin, Oscar Del Castillo, and John Fox are the other members of the team whose participation in this project has been both essential and effective to the development towards success of the mission. Our project stemmed from a need to shorten time delay and increase safety during takeoff and landing of all aircraft on the runway. Today, it takes on average anywhere between 2 to 4 minutes between aircraft allowed to occupy the runway as a measure of safety against wingtip vortices. These wingtip vortices form off the aircraft at takeoff velocities, creating circulation forces that drastically increase in strength with respect to the ground, making the atmosphere severely unstable for the next aircraft to attempt takeoff. Our project mission was to implement a system that could dissipate these vortices at a rate that not only shortens these time delays, but also does so in a manner that is safe and easily installed to all runways around the world. Here is our project poster. Please take a few moments to note some of the key points while I introduce you to our next speaker. Presenting the details of our primary subsystems is my fellow teammate, Riley McClurkin.
We chose the Hangar 9 Timber 110 RC plane based on the cost, size, and functionality. For a given budget, we wanted to maximize the size and speed while also using an electric motor because of its simplicity and consistency compared to gas motors, which can be difficult to start. The RC plane with the rimfire 1.7 Outrunner can reach a speed of 34 meters per second and has a wingspan of 2.79 meters. A challenge we faced was the disorganization of the electronics in the fuselage. By using Velcro and glue, we were able to allocate wires and objects to certain locations to provide easy access for pre-flight. The main challenge we faced was finding and correcting the center of gravity. The plane was tail-heavy and required placing weights in the nose of the plane in order to correctly balance the plane over the quarter cord. The smoke system we used was a smoke eel system from Germany. It came with 2 smoke emitters, a smoke driver, a fuel pump, and an oil tank. It is powered by a 6S LiPo battery. As you can see, the smoke system is attached to the wingtip with the fuel line and wires running inside the wing. Our first attempt to attach the smoke emitters to the wingtips involved square plastic command strips that held the smoke emitters with zip ties. Unfortunately, the high temperatures of the smoke emitters melted the glue and came apart from the plane. Before the COVID-19 outbreak, we had screwed metal brackets into the wingtips which we were going to zip tie the emitters to. And now John Fox will continue with the presentation.
The air-jet subsystem is composed of a compressed air cylinder, a brass adapter, a single-stage gas regulator, 2 heavy-duty air hoses, a switch, an electric pressure gauge, and a brass electric solenoid valve. The air-jet subsystem is expected to produce an output of 9 cubic meters of compressed air and have a total cost of $90. The cost, the portability, and the ability to produce a high velocity flow were the main reasons for selecting this air-jet subsystem. Experimental setup. The camera would have been placed on an adjustable 16.5-inch to 50-inch tripod. Our objective was to record 2 different scenarios, without the air-jet system and with the air-jet system. These observations would have been made from 2 different camera angles, from the side of the vortex and from behind. Software. To aid us with our vortex dissipation analysis, we would have used a proprietary software called Phantom Camera Control Application. This software has the capability of calculating distances. This is done by correlating distances in pixels with distances in a real-world scenario. Before any measurements, a calibration of the software must take place. This is done by defining the units and by using a calibration plate. The calibration plate that was used was a notebook with a height of 203.2 millimeters. It was placed approximately 1 meter in front of the camera. One of the measurements that is used to calculate the speed in which the vortex dissipates is time. The PCC software has the capability of calculating time between frames by inputting the first frame number and the second frame number, for which you want to measure the time lapse between the 2 specified frames. Vortex analysis. From the video without the air-jet system, we can see that the growth of the radius of the vortex barely increases. In other words, it has a constant vortex. This means that the energy is more compact. From the video with the airjet system, it is noticeable that the radius of the vortex increases at a faster rate. In other words, it has a fainter vortex core. This vortex has less energy. From the analysis, we can see that the software and camera system are adequate for our needs. From the images of the video that we presented, we can also see that the airjet system does dissipate the energy of the vortex.
The experimentation portion of this project consists of two separate but equally important sections of our mission. The first experiment is used to create a baseline for data. The RC plane and phantom camera will be set up as shown on the runway. The pilot will begin by accelerating the plane to its maximum velocity with the smoke system already initiated. Once maximum velocity is reached, the plane will pass by the camera where several images will be taken of the vortex smoke trail left behind. These images will then be processed through the camera software, creating the baseline for our analysis. Several trials will be done to determine the most effective position of the camera. After the baseline is created, we will then run the second experiment where the jet subsystem is now added to the side of the runway as shown here. Like that of the first experiment, the test will begin with the pilot initializing the smoke system and driving the plane to maximum velocity. This time, however, the plane will first pass by the jet system, causing it to activate and blow a stream of air centered at the core of the vortex. Meanwhile, the camera will take several more images of the phenomenon to later analyze and determine the effectiveness of the jet. Again, several trials would be necessary to find the best position for the jet with respect to the core of the vortex. Upon success, more jet systems will be added along the runway in order to dissipate the entire vortex the plane would leave behind. Unfortunately, due to COVID-19 restrictions, our team was unable to perform either experiment. We were able to test each subsystem individually. The camera, smoke system, and jet system were ready to be implemented in the field. However, the team ran into some issues regarding the RC plane that held up further experimentation. We hope in the future studies, design teams will be able to run each of these experiments and obtain data that can further satisfy the goals of the mission, following which should be iterations of these systems represented on much larger scales that can be tested on large aircraft in order to someday install accelerated vortex dissipation jets to all airport runways. The Vortex team would now like to thank our sponsors, the Simpson family and Dean Hahn, for the opportunity and funding to work on this project. We would also like to thank our mentor, graduate student Parisa Puri, for all the help and support she has given us throughout the year. Finally, we would like to thank Dr. Sergei Shakarev of the Aerospace and Mechanical Engineering Department at the University of Arizona for his time, knowledge, and dedication to the ever-growing progress of our project. Thank you, judges, for your time and consideration. If there are any questions, please feel free to ask any of the members of our team. Stay safe and healthy during this unique time of our history. Thank you.